Now I'm going to review the semiconductor device one. And first of all, I will talk about the quantum physics. That means the light have a wave and particle duality. Next, I will talk about the Schrödinger equation. And it is total energy is the kinetic energy plus potential energy. Next, the transmission probability. This is the electron through the barrier with the tunneling, and it is inversely proportional with barrier's length. And I will talk about the energy band. When there are lots of atoms, the loss of energy state will be overlap, and when loss of energy state overlap, spe- specific energy level will be full with the electron, and other energy level will be empty of the electron. So in this state, valence band edge means the highest level that is full with electron in 0 Kelvin, and conduction band edge is the lowest level that that is completely empty with electrons. So electron in 0 Kelvin. And for for the last, the forbidden band, it is in this band there's no electron, and we call the band gap. And next, I will talk about the insulator, and metal and semiconductor. When there is very thick band gap, we call it the insulator. And if the band gap there's no band gap, or it is turnover, we call it metal. And when there is approximately band gap, we call it semiconductor. So when we give the voltage, the insulator with the, when we give the voltage to insulator, the carrier will can very small of the small very small carrier will move, and metal, and when it is metal, the loss of carrier will move, and semiconductor, the appropriate carrier will move. Next, I will talk about the EK diagram. It is the energy is that through the reciprocities, and we can get the specific mass with the energy EK diagram. The and next I will talk about the DuPont. the silicon is the group 4 material, and when we give the group 5 material in the silicon, there will be the free electron because of the group 5 material. So this free electron comes to carrier, so we call it donor. And when we give the group 3 material in the silicon, one hole will make it, and this hole will be the carrier in the semiconductor. So we call it acceptor. We call it acceptor. Next, I'm going to talk about the Fermi Dirac distribution. And this is the probability that the probability of the energy that fermions can get. So fermion can get, and density of states is the C, or like how many electrons can get. So we can know the carrier concentration with these two multiple, and the carrier concentration per energy, we call it Boltzmann tail. And in this, we can know the Ni square equal N multiple P. So this means electron concentration, when there is many electron concentration, there should be small hole concentration, and when there is many hole concentration, it means there is small electron concentration. Next, I'm going to talk about the PN junction. In the circuit, we draw the PN junction like this, and the current direction is this like P to N, and when the direction is N to P, the currents will don't flow. And the PN junction's IV curve is like this, and I circle to the forward bias, and next to down to the zero is reverse bias, and zero we call equilibrium. And when we draw the Venn diagram of pin junction, we should draw it with these two P and N Fermi P and N's Fermi level with constant. And next, when it is forward bias, potential difference will be smaller, so the electron can move N to P, so IV level will be going up. And when the reverse bias, the potential difference will be more longer, so barrier this means the barrier are going bigger, so it means the electron can't move n to p. And last, for the last equilibrium, this is a barrier of the potential difference, so the electron can't move n to p. And next, I'm going to talk about the charge and electric field and electric potentials relationship. And when we and when we when we integrate the charge, we can get the electric field. And when we integrate the electric field, we can get the electric potential. And the next, I will want to talk about the heavily doped and lightly doped. The heavily doped, when we dope heavily, the deflation will be more smaller, and the light, when we dope lightly, more of the we can get more deflation. And for the next, I want to talk about the metal semiconductor. The metal semiconductor is we get metal and other N type or P type. So when we draw the Venn diagram of metal semiconductor, we should make Fermi level and metal work function constantly. So that Venn diagram should be like this when the semiconductor is N type, and when we do low when we do low doping, the IV curve will be similar to PN junction, and when we do medium doping, the reverse bias will be more low to the PN junction. And when we do heavy doping, it is like the line that is going up. And now I'm going to finish the review.